to this presentation about data-driven multilinear metro maps. This is joint work between me and Martin Nullenburg, and this is the long presentation for the Diagrams 2020 conference. So, a metro map is a schematic map visualization of a transit network that focuses on the topology of the underlying network rather than the actual geographic distances between the features in the metro map. Here you can see 4 examples, some of which are quite iconic. For example, on the top right you can see Henry Beck's London tube map. And all these examples have one thing in common, namely that they are in an octolinear layout. That means that all edges in the visualization are parallel to either the horizontal, the vertical, or one of the two 45-degree diagonal lines. But we can use different layout styles to visualize a metro map. Here is an example of a metro map of Washington, designed by Massimo Vignelli in 1973, that uses 3 drawing orientations. So here is an example of using a different number of orientations, which we will call k-linear. Here is an example of something that uses 4 directions, but the directions are rotated. The orientations are rotated such that the horizontal and the vertical orientation are not part of this map. And lastly, we could actually use a quite arbitrary number of orientations to which we schematize the input. And this will be called a multilinear metro map, and it has non-equiangular orientations. So let's look at these things one by one. First, let's look at k-linearity. What does that actually mean? Here you can see an example where k equals 4. So this is a 4-linear metro map. It's also known as an octolinear metro map. And every edge must be parallel to, as I already said, one of the 4 directions that are available: horizontal, vertical, the two 45-degree diagonals. But we can change that to the thing that we've also just seen, where we have a 3-linear metro map, which we will also call a hexalinear metro map. And now every edge needs to be parallel to one of 3 available orientations. And in general, in a k-linear metro map, we draw all edges parallel to a set of k available drawing orientations. The set of all valid and available orientations is called an orientation system. In this work, we consider 3 different kinds of orientation systems, so let's look at them one by one. The first one is an aligned orientation system. That's the first examples that you have seen, where you have fixed orientations. Consecutive orientations have a similar angle to one another, and the horizontal is part of this orientation system. Next is a regular orientation system. We still have the fact that the consecutive orientations have an equal angle between them, but we can rotate the entire system. And finally, we have an irregular orientation system that corresponds to the multilinear metro map that you have seen on the example slide. And here every available orientation has the freedom of rotating however it wants, basically. Okay, so this leads to the obvious question: if we have the choice of these different orientation systems, and specifically if we have a choice inside these orientation systems, how do we choose a good orientation system? Well, we can try to choose it based on the input geometry. This is where the data-driven part of the table comes in. So let's look at an example of how that will work. Here we have an input graph, and we have just a given orientation system. And we want to be able to judge how well this orientation system fits the input. And we can do this by taking the edges and placing them over this orientation system. Then we measure the angles of the edge with all the available orientations. So here you can see we have an angle, a smallest angle between the edge and an available orientation of 20 degrees. And we define the smallest angle as the distortion for this edge. Then we can do this for all edges in the input. And if we sum over all the edges in the input, we get a distortion value for this orientation system with respect to this input graph. And now we define an optimal orientation system as the orientation system that minimizes this distortion. Okay, so we have seen that we can choose a good or an optimal orientation system based on the input geometry, and we want to minimize distortion. So how does that work in the three different orientation systems that I have presented? Well, in an aligned system, we don't need to choose because here everything is fixed. We have a fixed orientation, the horizontal, and the offset angles are also fixed, so we cannot change anything, so therefore we don't need to make a choice. For the regular system, in which we can rotate the entire system, we basically have one choice. How far do we rotate the system? But we have possibly infinite possibilities for this. And we present a proof that we actually only need to consider as many orientation systems as there are edges in the input. And I will now present a proof sketch. So assume this is the orientation system, which claims to be optimal, and it does not coincide with any of the edges that are in the input. Assume these three edges are the only edges that are present in the input. But then we can identify all the edges which are to the right of the orientation that has the smallest angle between them, and all the edges that are to the left of it. And if this number is not equal, so here we have more edges that are to the right of its closest orientation than the ones that are to the left, then we can always rotate the orientation system, in this case clockwise, and this decreases the distortion of more edges than it increases the distortion of some edges. So here we have a counterexample of this orientation system being optimal. So what in case if we have the same number? Well, then actually we do not change the distortion of this orientation system by moving it clockwise or counterclockwise until we coincide with a single edge. So the takeaway is that we can always choose an optimal orientation system in which at least one edge coincides with one of the orientations which are available in a regular orientation system. So what about an irregular system now? Here we don't have to make one choice, we have to make k choices. For every single orientation we need to decide on the orientation that we want to apply. On the rotation that we want to apply. And we can also solve this by taking all the edges which are present in the input and taking the lower station and overlaying them, and by that creating a kind of a fan over the x-axis. And then we take the angle between an edge and the x-axis to the right. So here we have the list of all the angles which are present in this input. And now we can consider these angles as points on a line from 0 to 180 degrees. And now you could see how we want to cluster them such that we have a good representative for each cluster. So if we want to have a 3-linear layout, then we want to have 3 representatives that represent this set of angles the best. And a very obvious solution here would be 20 degrees for the first two, 98.5 degrees for this third and fourth, and just plain 160 degrees for the fifth one. And this is nothing else than a k-means algorithm. And Nielsen and Nock showed in 2014 that the one-dimensional k-means can actually be solved by a dynamic program in n² times k time. So this is also pretty good. As a summary, we have no choice to make for the aligned system. For the regular system, we have O number of edges in the input. And for the irregular system, we can use a dynamic program that uses n² times k time. Here is a big caveat that I need to mention, and that is that we minimize distortion for every edge individually. That means that every edge has the best possible representation by one orientation that is close to it. That is not a guarantee that in a computed map with additional constraints we can actually use this orientation to draw the edge. And that might mean that we have kind of covered an edge with a good orientation, but in the output it needs to choose another one, so it actually travels farther in angle than it would have in the classical aligned system. This is still a possibility. Okay, so next I want to talk about how we actually go about generating these metro maps automatically. And we can use automated methods to create high quality metro maps. And here I want to present the quality criteria that we have to judge the quality of a metro map. Not only we, but actually an automated system can use these quality criteria to judge the quality of a metro map. So first are a couple of requirements. Those are so-called hard constraints. These are things that a metro map must fulfill, otherwise it is not a valid solution. So first, every line segment must be k-linear. This is obvious, and we have already seen that this is something that we want in an output metro map. Second is we want to preserve topology. This just means that if we go in a circle around a station, the encountered edges must be the same as in the input. So on the right we have blue, blue, orange, orange, which is not the order that we have in the input, so the right solution here is not legal. Next is that line segments must have a minimum distance from each other. This has two reasons why we do this. One is we want to keep unrelated geographical features far apart, so we don't create artificial adjacencies between things which are actually not close to each other in the real world. And second, we also don't want to create crossings between lines where there are no stations. And fourth, every line segment must have a minimum length. And here the minimum length is to create a more legible metro map, because everything is nicely spaced, but also because you will see in the next step that we also want to minimize the length of every single edge. This minimum length gives us a kind of bottom line for everything. And together this leads to a nice distribution of stations over a line. So these were hard constraints, and now we go into the things that we don't necessarily need to keep, but we want to optimize for. So we want more of this rather than less of this, even though both might be valid solutions. The first one is line straightness. You can see that there are lines running through this transit network. So here is a green line, a blue line, and a red line. And across a line, we want to have as few bands as possible. So on the right, we have just straight lines, which is obviously better than all these squiggly lines on the left. The next is topographicity. This is a big word that just means that we can identify a somewhat natural orientation that an edge wants to have of all the available orientations. And if we are able to draw the edge in this natural orientation, then this is good for us. We might allow for some deviation, so maybe one orientation to the left, one orientation to the right, and we might even forbid some orientations. So a deviation of 2 might be illegal. The third one is what I already mentioned. We want to optimize compactness, which just means every single edge segment should be as small as possible, and together with the minimum length for every single edge, this gives us a kind of bottom line and keeps the stations nicely distributed. Okay, so now we have seen what the qualities are that we want to have in a metro map, but what's the method that we use to compute them? We built upon an already existing mixed integer program, which was built by Nullenburg and Wolf in 2005, and we extended to be able to generate metro maps in different linearity and also to incorporate other orientation systems than just the 4-aligned orientation system. The benefits of this mixed integer program solution is that octolinearity is something that we can guarantee. So we have seen that it is a requirement, and with this solution we can actually guarantee it, which is not the case for every single approach of computing metro maps. And we also can quickly generate initial solutions, which are already high quality, even though they might not be optimal. And this brings me to the next point. What is a mixed integer program actually? It is an optimization method that uses rational and integer valued variables and then uses linear constraints and an objective function using these variables to encode necessary and desired properties of a metro map that we want to compute. A mixed integer program in general is NP complete, which means that we can't really hope for an efficient algorithm to solve them. However, there exist efficient solvers for reasonably sized instances as we encounter them in the real world. And as I already said, we don't always need to solve them to optimality because intermediate solutions tend to be already high quality. Next, I want to explain how we use specifically a mixed integer program to talk about metro maps. So first, we need to have a way to address the position of a feature in a metro map. Assume that we are again in a 4-aligned setting, so the classical octolinear setting. Then we would use these directions, which is a redundant coordinate system. You can see that x and y are present as z1 and z0 and z2, but there's also the diagonals present as z1 and z3. And in a general way, we can express any kind of z coordinate just in relation to the angle theta it has with the x-axis. This can easily be extended to encompass any linearity system that we want. Here you can see a 3-linear system. An important difference is that this 3-linear system and irregular systems in general will probably not contain the orthogonal directions to the orientations that we have already given. But we will need the orthogonal orientations to talk about things being on the same line. So here we need to encode additionally the orthogonal directions so the orthogonal direction for z0 is z0, This leads to the interesting fact that in the aligned or the regular setting, k equals 3 has to keep track of more orientations than k equals 4, even though it has a lower linearity. Next, I want to go through one constraint and how we initiate it and how it contributes to the objective function, specifically for the property of the selection of edge direction and minimum length. So here, in this scenario, we are given this edge uv, and we have identified a natural direction, which is the vertical direction. We are again in a 4-linear aligned system. And now for every single direction that we could draw this edge in, which in this case would be either the vertical or one of the two diagonals, 3 or 1, we create a binary variable alpha I. So we would have alpha 1, alpha 2, and alpha 3. All of these variables are together in this sum, and this sum guarantees us that exactly one of these 3 Boolean variables is set to true at any given time. We interpret this as this is the sector that we have chosen to draw this edge in. Now, to guarantee that this edge is drawn in exactly the direction that we want, what we do is we instantiate this constraint. Let's go through this step by step. First, we have the difference of u and v in the orthogonal direction, and on the right hand side we have a very big constant and something in parentheses. The right hand side, if you look at the parentheses, if alpha I is set to 0 and we have not chosen this direction, then we don't want to care about this constraint. So what happens is the right hand side becomes m, which is such a big constant that we know that this constraint is true no matter what the actual coordinates are. If alpha, however, is 1 and we have chosen this direction and need to consider this constraint, then the right hand side will become 0. And this constraint simply says that the orthogonal coordinate of v is the same as u or even bigger. But that just means that it's on the same vertical line or to the right. We want it to be on exactly this line, so we do the same thing with the inverted difference, which means it is on the exact same vertical line or to the left. And if both of those need to be true, we know that u and v are on the same vertical line. Next, we want to guarantee that they are not drawn on top of each other or too close to each other, so we enforce a minimum length on this edge. Since we know the direction we draw this edge in, we know which difference we need to take. Here it's the difference in the actual drawing orientation, so here it would be, let's say, 2. And then we say that the difference between v and u must be bigger or equal than the minimum length that this edge should have. And then again, we just have the same thing that we had before, something that makes this constraint trivially true if this alpha is not chosen, and therefore we don't need to consider this constraint. So this constraint says that if alpha I is set to 1, then the zi coordinate of v is at least le bigger than the zi coordinate of u, and we have our minimum enforced edge length. How do these things contribute to the objective function? Well, we can define this variable c for the edge uv, and it is this expression. This expression has first a sum over all alphas, and these alphas are multiplied by the number of the direction they correspond to. We know exactly one alpha is true. So this sum boils down to the number of the direction we have chosen to draw this edge in. In this second variable, this dir uv variable, we save the exact number of the natural direction. So this is the direction that u wants to be drawn in, the edge uv wants to be drawn in. If this is the same number, then we have the optimal solution, and this difference is 0. If there is an actual difference between these two things, then xi is not 0 but might be 1. If we allow more deviation, it might even be 2 or bigger. So what we do to ensure that most of the edges are drawn in their natural orientation is we sum over all the variables xi that we have created, and then we minimize this sum. We can do a very similar thing for the other two optimization goals that we have already talked about, straightness and compactness. Again, we define variables, we sum all these variables together, and we take a minimum. It is important to note that these optimization goals might be in conflict with each other. So what we do is we define weights which weigh these variables against each other, and let us also emphasize one optimization goal or the other dependent on the given input. Now I want to go through a couple of examples that were created with the system that we designed, and I will always give the number of total bends in the solution and the distortion per edge, which is the actual average difference in angle for every single edge between the slope it has in the input and the slope it has in the output. All these examples are the current metro system of Vienna. Here you can see a 3-aligned version, and you can see we have 16 bends and we have a distortion per edge. And if I now switch to the next one, which will be the 3 regular system, which is slightly rotated, you will see that distortion per edge actually increases, even though we have rotated this orientation system in a way that every single edge has a good representative. This is the caveat that I already explained, in effect, that even though we have good representatives, edges are not guaranteed to be able to choose these good representatives. Here we have an irregular system, and we can see something that we have seen across all experiments, that in general in an irregular system distortion is lower than in other systems. Now if I switch to the 4 aligned, 4 regular and 4 irregular systems, you will see that bends heavily increase. And this is due to the fact that with an increased number of linearities, but the same number of deviations to the left and to the right allowed for every single sector, we increase the number of forced bends that we need to take in a given layout. And lastly, I want to mention that we are obviously not bound to use only 3 or 4 regular, aligned or irregular metro maps. We could also increase this to a 5 linearity system. This brings me to my last slide. And in summary, we have seen that we can use a mixed integer program to compute k-linear layouts. With arbitrary orientation systems, we can derive orientation systems based on the input geometry, even though there is definitely work still to be done to find a better way to actually achieve this. Our experimental evaluation indicate that in general bends increase if one increases the linearity, and distortion decreases if one increases the linearity. And also overall we have seen that irregular systems tend to create metro maps with low overall distortion. And this is the basically the take-home message of this talk, and what we want to emphasize from our work, which is that there is probably no singular optimal metro map layout style, not in linearity and not in orientation systems, but there are probably orientation system and linearities which are more suited to certain inputs than others. So our system should be understood as an aid for designers to be able to explore more and more different layout styles before they need to delve into the work-intensive task of manually designing a metro map. Thank you for your attention.